Okay, so let's start the class. So today we will look at some more examples on proof by construction, and in particular we will talk about a proof that shows the set of real numbers is uncountable. So I will define what is meant by countable and what is meant by uncountable. And then there are the announcements. So first of all, we have released homework 4 this morning. So you should have received that in your email account now. The due date is next Thursday. And then we will have exam 2. Exam 2 will be next Tuesday. So next Thursday we will have a tutorial talking about the assignment solution. And then the Tuesday immediately after that will be the exam. So in this exam, it will cover all the topics about homework 3 and homework 4. So this will be about recurrence, right? Homework 3. And then homework 4 is about proving. So like induction, contradiction, general principle, and then proof by construction. Okay. So it turns out that the assignment this time that is very long. Okay, in the description. So I would like to spend some time telling you some of the idea or explaining what is meant by each question. So there are going to be 6 questions for this assignment. Okay, and then 5 of them we want you to complete. 1 of them is just for fun. Okay, so the first one is called Joseph's problem. So probably I have mentioned this in class. So this problem asks about, let's say there are n people, they're standing around in a circle. So each one has a label from 1 to n. So we have 1, 2, 3, 4, 5, 6, 7. Let's say there are 7 people here. Okay, and then by standing on this circle, we are going to do an elimination of the people one by one. Okay, so that only one left in the end. We are going to eliminate every second person. So this is the starting point. So if we eliminate every second person, so 1 and 2, I will eliminate 2. Is that okay? Continue 3 and 4, I will eliminate 4. 5 and 6, I will eliminate 6. 7 and then 1, I will eliminate 1. Is that okay? 3 and 5, eliminate 3. Eliminate 5, and then 7, 3, eliminate 3. Okay? So in general, if we have n people, we are going to spend n minus 1 rounds of elimination, and only 1 left. So we will let j of n to denote the survivor in the case that starts with n people. So in our current example, so we will then have j of 7. It turns out that it is equal to 7. Is that okay? So for question 1, we want to show that Jn is actually very nice. Okay. Jn is going to be equal to 2 times k plus 1, where this k is the largest. Okay, so it is the non-negative integer after deducting the largest 2 power from n. Okay, so for instance, j of 7, so 7, right? So 7, if I take out the largest 2 power, so it will become 3. Is that okay? Okay. And then 2 times 3 plus 1, it goes back to 7. So J7 is equal to 7. Okay. Okay? So for instance, if I have another number, let's say J10, so what would that be? J10. So according to this formula, so I will remove the largest 2 power from 10. So I will take out 8. Okay? So the remaining part is 2. So I have 2 times 2 plus 1. It is equal to 5. Is that okay? Okay? And then amazingly, okay, this is difficult to see. Okay, this is difficult to see what's meant by this 2k plus 1 thing. So if you give me a number, let's say 10, so I would first transform it to a binary number. So 10 in terms of binary, it is equal to 8 plus 2. Is it okay? It is 1, 0, 1, 0. Is that okay? So 1, 0, 1, 0. It is 10 in terms of 2. So how do you get k? So to get k, so this is n. To get k, how do we get k? Remove the largest 2 power, right? So we take out the first one, the leftmost one. So we get 0, 1, 0. So this will be the so-called k. Is that okay? So how do we get 2k? To get 2k, how do we get? So if this is k, to get 2k, it will become 0, 1, 0 to add 1 more 0. Is that okay? So this is multiplied by 2. Is that okay? And then how do we get 2k plus 1? To get 2k plus 1, we set the last bit to 1. So it is like 0, 1, 0, 1. Is that okay? And then the effect, it turns out that it is like you are moving the first one to the last position. So for any number n, the Josephus number for the Jn, let me call it the Josephus number n. For n, it is like make the number n into binary, move the leftmost bit 1 to the rightmost position. And that will be the answer. Okay. So for this question, we'll ask you to prove that this is correct. And there are some hints. So try to take out the hints and then it will be easy to prove it by induction. Okay, so this is question number 1. Okay. Question number 2. Okay, question number 2 is easy, okay. Easy to describe. So that question number 2 is, let's take a n-sided polygon. Okay, so let's say this is a hexagon. So we perform any kind of triangulation. So triangulation means that we are going to cut it into triangles by using diagonals. Okay, by using non-crossing diagonals. Maybe the triangulation is like this. So this is one possible triangulation, or we can have a different triangulation. Maybe this could be another one. This could be a different triangulation. Is that okay? Is that okay? So suppose that the diagonal are in orange, edges and the outermost sides are in green. We want to show that no matter what kind of triangulation that you are making, there is always at least two triangles that we form with two green edges. Okay, so here in this example, this is one triangle with two green edges, and this is another triangle with two green edges. Is that okay? And for this one, this is there's one here and there's one here. Is that okay? Is that okay? It makes sense, right? And actually, in some case, you may have three. So for instance, let's say this is another triangulation. Let's say this is another triangulation, and in this triangulation we have three triangles with two green edges. Is that okay? So we want to show that this is true whenever the polygon that we look at has at least four sides. Okay. Okay. And a hint, this one is easy to prove it by induction. Right? Simon, is it? For this one, we are going to use induction, right?
Yes.
Yes, yes, easy. should be easy. Okay. Okay. Now the third question. Okay. The third question says that, okay, suppose that you have a map, and then let's say there are paths joining different places. So this question says that if we have 2 points, let's say one of them, let me call it V1, and then let me call the other point V2. So we want to show that this fact is correct. So we want to show that this is what we want to show. There exists an integer p such that if there is a path from V1 to V2 with length greater than or equal to p, let's say greater, whatever. Then there are infinitely many paths from V1 to. So this is what we want to show. Well, this is some kind of strange. Okay, so maybe the graph is very simple. It's like this. So let's say this is V1. Okay, and let's say this is V2. Okay. Then this graph is just 3 vertices. Then, so Simon, is it if and only if? Well,
just copy the text.
Okay. So let's say if you look at this one, then what is the p that we want to find? So we want to show that we can always find such a p such that this is correct. Now for this one, so we can actually set p to be 4, because in this graph there is no path. Actually, path means no path. There is no path from V1 to V2 with length greater than 4, right? But if it happens, then the integer p equal to 4 will make this always true. So this one says if something, then something, right? But the first condition is always incorrect. So this will be always true. But on the other hand, so let's take a look of another possible case. So let's say okay. So for instance, in this example, there are actually infinite many paths from V1 to V2. So how can we get different paths? One is like V1 go to this one and go to this one, right? The other one is V1 go to this one, go to this one, go to this one, go to this one, and go to this one. This is another one. And then the other one is V1 go to this one, 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 and go to this one. Am I correct? So there are infinitely many ways from many paths from V1 to V2. So we don't require the path to be simple. So a vertex can be repeated more than once. Okay. So here in this question, it is like you want to show that for any graph, you can always find a certain p such that this is always true. Okay. So this is kind of an existence proof. You can tell p to be 100. You can tell p to be 200, whatever. As long as you can show that in your graph, when you put in the value of 100 or 200 here, then it works. Then it's okay. Okay. So this turns out to be, if you understand, so this question is just a strange question, but it is, the answer could be very, very simple. Okay, you just need to understand what this question is asking. So here is like, given any graph, okay, show that you can always find an integer p, such that, okay, if there is a path between any two vertices v1 and v2 with length greater than p, then it implies that there are infinitely many paths from v1 to v2. Okay, we don't need to find out the smallest p. This is the question. This is the point. Okay, good. Question number 3. Okay, question number 4 is this one. So question number 4 is, okay, so we have a grid, 3 by 9 grid. So we start with the 3 by 9 grid. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So that's a 3 by 9 grid. So these are the grid points. So you just join my edges. Okay. So we are going to color the points either by red or white. Okay. So we will color them. Okay. This is red. 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 Maybe they are always this red, 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 red. Okay. Okay. Let's say this is the case that we color. We want to show that no matter how we color, we are always going to find a certain rectangle such that all the corners of that rectangle is colored by the same color. So what is a rectangle? So this is a rectangle. So if we look at this rectangle, we want to look at the corners. This one, this one, this one, and this one. Okay, so in this case, this one, this one, this one, this one, they are not all colored by the same color. So this is not a good case. If you look at this rectangle, with this one, this one, this one, this one. So white, red. So this is not okay. But on the other hand, let's see. So if you look at this rectangle, 1, 2, 3, 4. Is that okay? So 1, 2, 3, 4. So in this rectangle, the 4 corners are all in red. Okay. So here in this case, we want to show that no matter how you color this, no matter how you color, how the reds and whites are colored into the points, you can always find a rectangle with same corner, with same color in all the corners. Okay, is that okay? So we will be looking at a larger rectangle, for instance, this one, this one, this one, this one. This is also good, okay? Because we just look at the corners. So intermediate edges or anything else, we don't care. Okay? Now, this one, it turns out that you can apply the general principle and easily show. Okay. Now, so there is a follow-up question here. So, if you want to do more, try to show that in case of 3 by 7, it is always true. So, if you have 3 by 7, no matter how you color, you can always color it so that there are rectangle with 4 corners in the same color. Okay. But on the other hand, 3 by 7, it is still okay. But on the other hand, if you make it a little bit smaller, 3 by 6, then there is a case that it is not okay. Not always okay. So you can try to show these two things in addition. Is that okay? Okay, good.